Okay, students. Now we are going to discuss a very important topic, and name of the topic is torque on bar magnet in a uniform magnetic field. You know that torque is the responsible for the rotational force. Okay. So the bar magnet, when going to place in a uniform magnetic field, then what is the value of torque? What are the factors are affecting this rotation? That we are going to learn in this chapter. So name of the topic is torque on bar magnet in uniform magnetic field. Okay, so we have to know about the torque of bar magnet in a uniform magnetic field. So for that, first I am going to draw a magnetic field. These lines are just represent the uniform magnetic field. If the uniform magnetic field is a B and we are placing a bar magnet with some angle in a uniform magnetic field, that is the south and it is a north, then what you are going to be observed there? We are observing that one force working on the north pole, it will have this direction due to this magnetic field, and over the south another force is working in the opposite direction of the applied. In this north pole, over the north pole, the force is working in the direction of magnetic field, but on the south pole it is the opposite direction of the applied magnetic field. So I will write here force on north pole. Kiske? Due to the magnetic field. So what is that? F equal to, if M is the pole strength of the north, then it is the product of MB. B is the magnetic field where we kept the bar magnet. And direction iska kya hoga? Direction is along the magnetic field. Along the magnetic field. Right? Along the direction of magnetic field B. When we taking the force on S pole, okay, in that case it is the MB, pole strength into the magnetic field, and it is the opposite to the magnetic direction of magnetic field. So opposite to iska direction, what the direction is that? Direction is just opposite to the direction of magnetic field. Now what we have to do that, if you observe here, the force is MB and here force is MB, but both the force working in a opposite direction. So suppose this one is the bar magnet keeping this way, and one force is making them down and another force making them up. So what happens? The rotation will come. When the rotation will come, then such rotation is called torque. So the torque T, it's not T but looks like T. So torque is equal to the either force, any one of the force into either force into perpendicular distance between two force. Means the either force means that is the what? MB. Now what is the meaning of this perpendicular distance between the two force? Here the two force, one is working in that direction, another is working in this direction. So the distance between these two forces, and which type of force? That is the perpendicular. So if I will draw such kind of diagram, then this one is called perpendicular distance. If it is a k, then nk is the perpendicular distance. This nk, here the k, and this one is the n. So this one is called perpendicular distance. And this perpendicular distance in between this pole and this pole, you can say that in between this force and this force, right? So here the angle is 90 degree because it is a perpendicular. Now, so what is the meaning of kn? First I will write here, it is equal to the kn. Now what is the value of kn you will draw? Now what you have to draw, just do one thing, that you take this diagram in such a way. Here n, here s, here k, and it is a 90 degree. So what you are observing that this one is the length of bar magnet, and length of bar magnet always going to be taken 2L. So this one is the value of 2L. Okay, and this value we have to know. So what we have to do? We are doing that sine theta equal to what? Equal to Kn by Ns. So Kn equal to Ns into sine theta we can write. We can write or not? We can write by the help of trigonometry. So what I will do here, one more step. Mb into, in place of Kn, I will write Ns sine theta. Right? Now, when we write this Ns sine theta, so we will put the value here. So I am rubbing this area. So what I am doing that? I am taking this value to the up. So torque equal to Mb into the Ns value is 2L because Ns is this 2L and sine theta as it is. Now can we arrange somewhat like that? B into M2L sine theta. And what you know that by the help of this equation, this M2L is equal to the B into capital M sine theta, because we know that M2L is called magnetic moment, and the magnetic moment of bar magnet it is called. So 2M M equal to M into 2L equal to M, that is a magnetic moment of bar magnet. So now this one will come. So it is better to mention dot. Everywhere I mention the cross, better to mention the dot. Okay. So now this one is the torque. If I will write this one in a vector form, then what the result will come? Torque equal to vector V cross vector magnetic moment M. We can write this one. This one is the vector form. This one is the vector form. Vector form of what? Torque on the bar magnet. The torque working over the bar magnet we can write in this way. So this one is the torque B dot M sine theta, vector form B into the magnetic moment, that is. Now what you have to do, we go for the another information by this one. I will take this value again. So torque equal to Bm sine theta. Now do one thing, let theta equal to 90 degree and magnetic dipole moment M equal to, you can take that 1. So when we put the value here, what you will get? Torque equal to, here B means magnetic field equal to unit Tesla. So what we have to do that, when we put the value here, then what we are getting the result? Torque equal to capital M. Torque equal to capital M. Means if the bar magnet going to keep a perpendicular to the uniform magnetic field, and the value of uniform magnetic field is the unit Tesla, in that case, the numerical value of torque is always equal to the numerical value of what? What is the M? Magnetic dipole moment. So both the numerical value is the same when this condition are going to fulfill this condition. Clear? So numerically it going to be same.